Alright, so for the 22nd day, we are given a map that looks a bit weird, and we are also given a sequence of moves and rotations that we can make on that map. So basically, the map will have empty spots that are represented by the dots and walls that are represented by hash symbols. And the idea is that we can walk forward given by the amount of steps that is specified in the input, and after that follows a letter, an R or an L, that tells us to turn to the right or turn to the left. So the main trick of this question is that the movement is wrapping around the map. So basically, if you move forward and hit the edge, then you would go back to the beginning and continue from there. And yeah, the rule still applies. If you hit a wall, then you stop in the previous spot. So the question is, for the first part, if we do this entire type of movement, where are we going to end up? So basically, we have to multiply the coordinates of our final position with some numbers and add everything up, and also like add the direction of that we are facing. Then for the second part, actually this entire map is a cube, so the spots on the input represent the faces of the cube. So what we have to do is, instead of wrapping around the map, we have to wrap to the next face that it's adjacent to this face. And yeah, I mean that makes it a bit difficult, but I mean, I'm not really sure how to solve it in a way that would work on any input. Like probably solving it in a way that's hard coded for each person's input would be the easiest solution. So but the answer should be like the same thing: the coordinates where you end up multiply with these numbers, and that would be the final password for the monkeys. So yeah, basically I thought that we should keep the map as a hash map, and in this hash map we keep the open tiles and the wall tiles. So we just have to enumerate all the lines and all the characters in each line, and we just build this hash map and keep only the characters that are either dots or hash symbols, and also parse them into their respective tile type. Then to parse the moves, I split that line of movements into characters, and then I grouped everything by the is alphabetic predicate. So basically we'll have a list of lists, and each list will contain either only letters or either only numbers. So we convert each set of characters into a string, and if that string is an R, then it means that it's a rotate movement in the right direction, and if it's an L, it means it's a rotate movement in the left direction. And otherwise this should be only numbers, so we can parse everything into an I size. Then to parse the entire input, we just split by double new lines, and then parse each component of the input. So first parse the map and then parse the moves. Then I created this dir enum to represent the direction of the player, like what direction are we facing, and I have created this helper method dir to delta that will return the delta for the xy coordinates representing this direction. So 0 1 for right, 1 0 for down, 0 minus 1 for left, and minus 1 0 for up. Then I also implemented this dir rotate function that takes in the direction and the rotation and gives you a new direction. So if the rotation is to the left, then you have the four cases. Depending on which direction you are looking at, you have to rotate counterclockwise, and if you receive the rotation to the right, you have to rotate clockwise. Then for the first part, I have simulated like every move. So this function will receive as input the move, the map, which is just that hash map of points, and the current state, which will be a tuple of three elements: the position and the direction. So first we compute the delta that we are required to move to. So depending on the move, we can have either a step or a rotate. So in the case where we have a step, we first compute the delta depending on the direction, and then for each step that we need to make, we have to keep the previous position and the current position. So if the current position is over an empty tile, like the dot, we just update the previous position to the new one and go to the next step. However, if we encounter a wall, then it means that we need to stop and just return the previous position. And the last case, which is a bit more tricky, especially for the second part, we need to loop back to the beginning of the hash map. So the easiest way, I guess, to do it is just go in the reverse direction. until we find the edge of the map. And then there are again two cases. If the first tile is open, then we just do what we did previously, we just move to that position. But if the tile that wraps around is a wall, then it means that we can't wrap around the map. You have to stop. And in the case that we have rotate movement, we just rotate the direction, and that's all. So for the first part, we just compute the beginning of the map. That will be the first row, and then we have to compute the start column as the minimum value on the map. So I mean, depending on each person's input, it could be different, but for me it was, I think, 50. And then the start direction should be to the right, and all this starting thing represent the initial state. So we have to apply all the moves and then just apply the multiplication that was stated in the problem. Alright, so for the second part, I was trying to hardcode the solution for my own input, but I realized that would be a bad solution, and I managed to figure out an idea of how to do it in a 3D space with rotations, but I wasn't really able to figure out how to do the math behind it, and I found the solution on Reddit and I copied it, so I cheated a bit, but I think it's fine. So the person that I stole the code from used this glam crate, which is used for graphics and games, and so I converted my map of tuples to a map of ivex to make things easier. Then I computed the width and the height of the entire shape so that we can compute the size of a square. Basically in the example it's 4, and for our input it's 50. Then I created this skeleton hash set that will hold the indices of the square that build up the cube. So basically we have to iterate from the beginning up to the number of squares that will be on the x and the y axis. And if our hash map contains one of the points that are inside one of these squares, then it means that this square is part of the skeleton. Then we are going to do a breadth first search, and we are going to start with the top left face. So we remove it from the skeleton and add it to the search queue. So this queue will be a list of tuples from that will have the faces and the rotation matrix for that face. And we are also going to build up this cube chart hash map that will have as keys the 3D position of the point on the cube, and as a value the 2D position from the regular map that we received as image. So the first step, which is the one that I wasn't able to do myself, was that for each point on the face we have to rotate it to the correct position. So at first I was thinking that we should probably just multiply the point with the rotation matrix, but this didn't work. So what I found that the author did was to first translate it and then divide everything by the square size, so basically moving it in the unit cube, and only after that he rotated the point. So basically I think that the idea is that you have to translate the face up with 0.5, and then if you rotate it, it will be in the correct position in its right rotation, and then you have to translate it back to the origin and also multiply everything with the square size to project it back. And then in the cube chart we insert the point and its coordinate in the regular space. So we multiply the face with the square size to find the right square, and we add the offset to that position. And then we have to visit all neighbors, so the right, up, left and down neighbors for this face on our map. And if the skeleton contains that face, then it means that we can add the current face to the search queue and remove it from the skeleton. And the rotation matrix will be the old matrix multiplied with the corresponding XY rotation. Yeah, I'm not really good at explaining how this rotation works, but you can imagine that if the face is upwards compared to the current position, then it means that we have to rotate it on the x-axis because it has to fold down. If it's to the right or to the left, we have to rotate it on the y-axis because it's vertical, but the rotations will be like mirrored. So if it's to the right, you have to rotate it counterclockwise, and if it's to the right, you have to rotate it clockwise. And if it's on the bottom, you have to do the same as for the top, but you have to rotate it counterclockwise on the x-axis. Then for the easier part, which is basically what I did in the first part as well, we have to go through all the moves, but this time when we encounter left or right, instead of rotating with the map, we have to rotate a 3D direction. So we do it by using the cross product, and to rotate to the left or counterclockwise, we have to do the cross product with the negative value of the up vector or the normal vector on the face, and to rotate to the right, we have to cross product with the normal direction on the face. Then we do the same thing, we do each step individually, but if we go off the cube, then what we need to do is to basically, instead of moving in the forward direction, we have to move downwards because that's the direction, that's the new forward direction. So we update everything like that. And yeah, if you understand that the new up direction will become the previous direction, then it's fine. It's like the new normal on the new face that we are going to land on will be the previous forward direction. And then as before, if we find the wall tile, then we stop, and if we find an open tile, then we update the previous positions. Then we get the chart position, basically the 2D position from the 3D position that we landed on, and it's pretty easy to multiply the x and y coordinate, but it's more difficult to get the new facing direction. So to get the facing direction, we need to keep track of the previous position, and we need to basically compute the direction delta. So yeah, I mean, the idea is that take the previous position in our walk, and we get its 2D coordinates, and after that we will be left with one of these types of directions, and yeah, that's the facing direction that we need to add to our value. So yeah, this was day 22. I think it was difficult for me, especially to make it more generic and not hard code the solution, but it was also interesting to learn something new. So yeah, if you want to check the code or also the code of the person that I stole the solution from, I leave both in the description. And yeah, see you guys next time.